Alrighty, let's just go ahead and jump in. So thank you everyone for joining us, and thank you, Sherry, for the introductions again. Um, so the title of our session today is Biostatistical Concepts and Examples. And again, the session is led by me, Alicia Lozano, and Dr. Tanya Locklear from the Heart team. So go ahead, next slide, Tanya. So here are our learning objectives for today's session. And so first, we're actually going to start off with providing an overview of the statistical support that is available through our groups at Virginia Tech and Carilion Clinic. And then we'll dig into fundamental topics in biostats, including things like hypothesis testing, alpha, beta, and power, as well as different types of statistical tests for both normally and non-normally distributed data. So we'll hit on p-values, effect sizes, distinguishing also when to use relative risk versus odds ratios. And we should have sufficient time for questions at the end, but if you do have immediate questions, you can raise your hand or put it into the chat. Yeah, next slide, Tanya. So first, we'll dig into our groups and how we can potentially support you in your work. Next slide, Tanya. So for both sites, you'll see contact information as well as website links for you to visit in your own time. And so as you all know, Heart is directed by Maddie Tenzer and recently managed by Mariana Salomon. And so the team itself is employed by Carilion Clinic, and I believe, which I just learned today, that all employees are remote. But work together very cohesively. So here on the left side, you'll see some photos of the Heart team. And CBHDS, with our team on the right-hand side here, was founded and directed by Dr. Hanlon, Dr. Alexandra Hanlon. And so our center is physically located in Riverside 4 of the Health and Sciences Technology campus in Roanoke. But we are, interestingly enough, academically housed within the Department of Statistics within the College of Science, which is in Blacksburg. So a little bit complex, but this is our both of our teams here. And again, our contact information and links to our website are here for you all to use as at your liberty. Next slide, please.
So the statistical support that's offered, we're going to go through and discuss what that looks like within each of our different programs. For my team, for Heart, we have about 20 members on our team. We support, provide end-to-end support of the research process. We have grant-funded and institution-supported research. So we do a lot of work also with QA/QI projects. We do work with, clinical research, as well as grant-funded projects. We have a lot of us have been here for several years. I've been here with Carilion for 8 years now. We support all of the different areas like research informatics, biostatistics, data science, all the different things that are available. But we also do data extraction where we can pull data for you in terms of like EPIC data and so forth. But let me get into that one in a little bit on the next slide. I would also say that we have virtual office hours every Tuesday from 10 to noon. And there is a link here that you can use. You can also reach out to our Heart team, heart@carilionclinic.org. And then that would give you, they could also give you the link to the office hours as well. When we do have the office hours, we have at least 1 or 2 people on each time, and they could be someone that has had a little bit more experience with data extraction or someone who has had a little bit more experience with biostatistics. So we share that load, but they can always reach out to other people if there's additional questions that maybe they don't have as much experience with in one area or the other. So here's our end-to-end research support. I've shared this link as well, and this would be one of the links that I would say, the red cap link at the top right of the page, because that link is a link to something called My Project Path. And that particular link will allow you to go through a guided step-by-step process of the resources that are available for Carilion. And so we have information on there about R&D, the IRB. We have information about study designs. We have some biostatistical videos that are available in case people wanted to go back and look at some information regarding, how to do a t-test or how to do chi-square test using SAS Studio, things like that. So we have some videos that are out there. We're planning on adding more to it. So as you go in and look at our website for the internet website that we had previously, that particular one is still being built and developed. So there's a lot of information that will be brought on. We work with you on extracting data and using Trinetics. And we build information through REDCap for survey analysis. And then we also support any of the analyses that you would need, and also the presentations as well as manuscripts. So again, end to end, and we're here to help in any way that we can.
And our CBHDS team has grown anywhere between 15 to 20 team members consisting of biostatisticians, bioinformaticians, epidemiologists, programmers, data scientists, as well as undergraduate and graduate student interns. So our numbers do tend to fluctuate depending on number of projects and grant funding that we have. Our center was founded in 2019, so we are a young center. I wouldn't say we're new, we're young. And so we provide expertise to projects led by Virginia Tech researchers and beyond. So that can include Carilion Clinic investigators as well, who have appointments, for example, at the School of Medicine. And so we collaborate with investigators on matters related to study design, power and sample size estimation, grant proposal writing, statistical programming, other things like data visualization, statistical analysis planning, data analyses, also the preparation and submission of abstracts and manuscripts and so much more. And so we also aside from that, provide data management support. So writing data management plans for federal funding like NIH grants, for example, designing databases, whether that's in REDCap, Qualtrics, and so on. And lastly, we do engage in teaching, mentoring, and advising activities such as this, and delivering guest lectures, workshops, and webinars. Next slide, Tanya, please. And so within a team science model, our CBHDS team does serve as short-term consultants or long-term collaborators. And so specifically for short-term consulting, we do offer Zoom drop-in hours 4 days per week, 2 times a week. And so, 4 days per week, I should say. That just recently changed in the spring, where we added 2 additional days. So these drop-ins are appropriate for questions that can be answered in less than an hour's time. And so our drop-in hours are supported by the Fralin Life Sciences Institute for bioinformatic hours. And the School of Medicine at Virginia Tech for medical student hours. And then lastly, by our iThrive CTSA for general drop-in hours, which are open to anyone, no matter what institution. And so we do encourage longer-term collaborations and obviously in the spirit of strengthened partnerships in science. And for single projects, when possible, we do strive to work with investigators from study design through data analyses and the dissemination of results of those projects. And so our goal is to transition from project to project with our collaborators and essentially building programs of research. So next slide, please. And for longer term collaborative projects, one of our team members may be funded to work solely on that project for a set percentage of our time and over an extended period. That can be weeks or months, depending on the needs of the project. And in situations where we collaborate on grant proposal submissions, we ask that investigators connect with our business manager to prepare a budget. And what we try to do is really emphasize that we strive to work with investigators also from design to dissemination, very similar to the way that HEART works. And for funded awards, we always work within a team science model, collaborating with the research team on issues related to, study design, database setup, and so on, all the way through dissemination. And we generate summaries for annual reports, that are needed to be submitted for the funder. And when applicable, we also generate data safety monitoring board materials for open and closed sessions as well. So lots there. Thank you. So then let's just dive right into the statistics unless anyone has any questions about any of that. We can just dive right in. Just pause for a second. All right. So this slide here provides an overview of essentially two main types of statistics that are used in research. So that's quantitative and qualitative, with each type serving a different purpose in data analysis and interpretation. And for descriptive statistics, so under quantitative statistics, we have descriptive statistics, which essentially summarize and describe a specific data set. So they don't allow us to make conclusions beyond the data that we're given, but they do give us insights into its main features. And so common measures of or descriptive statistics can include like a mean, median, percentages, standard deviation to, examine your spread or variability in your data. And so an example of this, if we were to survey a group of people on their smoking habits, we might report the median number of cigarettes smoked per day, for example. So that would be a descriptive statistic. And then the second type of quantitative statistics is inferential statistics, which go beyond simply describing your data and really allow us to make generalizations about a larger population based on our sample. So the type of statistics, essentially inferential statistics involves taking a sample from a population and using that sample to make inferences or draw conclusions about the broader population. And so in that same smoking example, so in a smoking study, we might use inferential statistics to estimate the smoking habits in an entire community based on our sample data. And so just looking at this visual here on the right side, we have an illustration showing the process of sampling. And so a large group of individuals represent the population from which a sample is selected. And descriptive statistics describe that sample, while inferential statistics use it to make broader conclusions about that population. Okay. And qualitative statistics. So unlike quantitative data, qualitative data is non-numerical and includes observations, words, and descriptions. And so this type of data really helps us to understand the why and how behind certain behaviors or outcomes. So again, in that example that we've been going with in a study on smoking, qualitative data might include personal interviews where participants describe their reasons for starting or maybe quitting smoking, for example. And then lastly, triangulation here is essentially a process where multiple data sources or methods are used to ensure the accuracy and credibility of findings. And so in qualitative research, triangulation often involves combining observations, interviews, and other qualitative measures to validate your outcomes. And so both of these types of statistics are crucial in research, and quantitative statistics really give us measurable data, while qualitative statistics provide that depth and context. And together they provide a comprehensive understanding of your research questions. Next slide.
So now we're going to switch over to hypothesis testing and focus kind of on the quantitative side of the statistical analysis that Alicia was just referring to. So in hypothesis testing, you start off with a null hypothesis and an alternate hypothesis. So in your null hypothesis, it could more or less be your standard of care, the impact of the intervention that you're getting ready to apply would have no significant change to the outcome. So if you're looking at a study where you're comparing a new drug that's being tested for, let's say, hypertension, then your null hypothesis would be that there is no difference in that particular drug's impact on hypertension compared to the standard of care with drug A. That's the one that's been used most often or has been used in the past. But with an alternate hypothesis, you have some reason to believe that there is going to be a difference in this new drug and the impact that it has on hypertension. So your alternate hypothesis is showing that there is an impact of this intervention is going to make a significant change in the outcome, a significant change in the systolic blood pressure of a patient. So there are two different types of looking at this, and we're going to get to that on the next page. But this example is showing that the null hypothesis means there's no difference, where the alternate hypothesis means that there is a the means of these two different values for systolic blood pressure is not the same. So we are assuming that the null hypothesis is true because that's what our background is. That's what our previous experience has been. And then our decision based off of whether or not we end up with a statistically significant difference will be to either reject the null or to fail to reject the null. So we're showing that one is supporting or not supporting the null hypothesis. And that's how you go through a hypothesis testing. So the reason why I was mentioning before what happens with the different types of alternate hypothesis, you can have two different kinds. And the two different kinds determine whether or not you have a one-tailed or a two-tailed test. So when you have an alpha level of significance, the question here is, what does alpha actually mean? So it addresses the role of chance. We set this at the very beginning of a study, and we say, okay, we are going to allow ourselves to have a 5% chance that our results are a result of chance and not because of the intervention that's being applied. And we are allowing ourselves to have this 5% level of chance. In this case, if we have a two-tailed test, which is very similar to what we were just saying, the drugs is going to make some difference, but we don't know whether that difference is going to be higher in the systolic blood pressure or lower. So we would have what's called a two-tailed test. In a two-tailed test, your 5% alpha is split in half. So 2.5% is on one side and 2.5% is on the other. In a one-tailed test, you may say that you think that the mean of the systolic blood pressure of the patients on drug X is going to be higher than the mean of the systolic blood pressure of patients on drug A. That would be your null hypothesis, that there's not going to be a change or it's going to be higher. But our alternate is that it's going to be lower. And so we're looking at a one-tailed test on the lower end. And this would be where all of our 5% of our alpha is going to be. Most of the time for the research that I have worked with, you do not usually see one-tailed test. And the reason is because we really don't have enough background or research support to say that we truly believe this is going to be less than or greater than the other one. A lot of times we're just trying to see, is there a difference? And if there is a difference, then we can look to see whether that's lower or higher. But we have a reason to believe that we think it's going to be lower, but we usually have that as a two-tailed test. So the type 1 error is what you are also willing to make. That's that 5% level. I'm going to get into the type 1 errors in a couple of slides, but that's where this alpha comes into play. So it's the role of chance in your study. It's the probability of rejecting the null when it's actually correct. So we're allowing ourselves to say that we have a 5% chance that we're going to think that the intervention is working when it actually is not. And then also it means that 5 times out of 100, we're going to say that the effect from our intervention was there when it really was not. So that 5% level is the generic level that we usually use. And what ends up happening, though, is you could have someone choose a 1% or a 10%, but you have to pick that from the very beginning. And sometimes like a 1% may be someone is developing a drug for, heart failure and things like that. And because of that, you want to be 1% chance that you are going to get that wrong. So there is a reason for choosing some of these different levels, but for the majority of us, we usually use the 5% level of significance. This is an example of what the slide looks like for beta and power. You hear us talk to you, or you have researched and also reached out to biostatisticians for help on how do we get enough power for our study. Well, what does power and beta mean? In this graphic, what you'll see is that power is this portion over here in the purple. Beta is this portion over here in yellow. And this portion that's red is our alpha. So this is our 5%. So this is an example of a one-tailed hypothesis test where we have the alpha is on the upper end of this. And when we are looking at this, the statistical power is the ability to detect the effect of the alternate hypothesis that actually exists. We have to have enough power so that when we find this mean, that we'll know that it's actually statistically different than the mean of the null hypothesis. So these are two distributions. This is our null distribution, and this middle would be our mean. And then this is our alternate distribution, and this line would be our mean for the alternate. We want to know if these two lines are statistically different from one another. Are they so far away from one another that they have to be in two different distributions? And when we're looking at this, as long as your mean falls within the alpha, then it's going to be supporting the alternate hypothesis, and you have enough power. So if your results are significant, then you did have enough power to reach your result. If, however, you don't have enough power, then it could be that your beta is too high. So beta is the probability of rejecting the alternate hypothesis when it's actually correct. And the distance between these two peaks is what we refer to as the effect size. So we're going to get into that one on the next slide or two. But what happens is when you're comparing these values, we need to know how big of an effect is this going to be. I have an example. Suppose you're looking at mortality. So if you're trying to do a study where you're trying to reduce mortality, and your mortality in one group and the null hypothesis is 27%, then an alternate hypothesis, we may be able to find a nice sample size that will allow us to determine whether or not this change is statistically significant without having to have a super large sample size. If that null value, the mean is 1.8%, for example, the distance between these are going to be so small that we have to have so much more sample size to be able to find that difference. And so an effect size has to do with not only the actual value of the null, but it also has to do with how close these two peaks are. So those are the questions that we would refer to, and when we're trying to talk to you about determining your sample size and to make sure you have enough power for your projects. So then what is the p-value? Well, the p-value is a probability of an observed point estimate that is extreme as a calculated value. So when you have a p-value, and let's say your p-value is 0.4, well, just 0.04, if you have a p-value of 0.04, then that means there is a 4% chance that you could pick a random value that is just as extreme as that one, but is not based, but with knowing that the null hypothesis is true. So it means it had nothing to do with your alternate hypothesis. It had nothing to do with your intervention. So that's a very small chance. So when you have a p-value, it's determining that probability of finding a value that's just as extreme, but knowing that the null hypothesis is true and that had nothing to do with your alternate hypothesis. And that's the reason why we use the p-value of 0.05. And then if we are less than that, then we think that our null hypothesis has not been supported, and our alternate hypothesis has given us enough information to be able to support that, and that our intervention did the right thing or did what we were hoping. Now we have the type 1 and type 2 errors. We've already addressed that a little bit in the conversation, but the type 1 error is the probability of alpha. So we have a 5% chance that we think that the alternate hypothesis is true when the null hypothesis is actually true. And we have our power is when we actually hit the right idea. So we thought our alternate hypothesis was supported and our alternate hypothesis is true. So for a lot of our projects, we're looking at 80% power, 90% power. If you have an 80% power, then that means you have an 80% power here that is going to say that your alternate hypothesis is supported and your alternate hypothesis is true. If we end up having our null hypothesis supported and the null hypothesis is actually true, then that's our 1 minus alpha. That's our 95% chance. So we have a 95% chance that if our null hypothesis is actually true, we're going to find that it's actually true with our data. In our type 2 error, this is where we believe the null hypothesis is supported, but we found that there is a statistically significant difference and our alternate hypothesis is true. So what ends up happening is that's our power. So this is going to be our probably this is, I'm sorry, it's 1 minus power. This is going to be our beta. So if this is 80% power, this is 20%. You would like your power to be 80 to 90% because that reduces this idea of having a type 2 error. So the type 2 error is where you think the null hypothesis is supported by the study, but the alternate is actually true. And so that's just, it's looking at these different things and helping us. We try to help you determine which way is the best way to go with your power and with your sample size, because the only way to really increase power is to increase your sample size for the most part. And those are things that we would talk to you about as we're moving forward. And now going back to the effect size. Remember, the effect size has to do with the two peaks. How close are they together? If those two peaks are very close together and you're trying to determine whether or not there's a difference between something that has, let's say, a mean of 29%, and then on the other peak, you end up getting a mean of 28%. Well, that's probably not going to be statistically different unless you have a very large sample size. And so we try to estimate the effect size at the beginning. How would we really know what that means, what that effect size is going to be? Well, we'll ask you, is there any research that you can share with us that have tested something very similar, or that maybe we could use to help determine the effect size between these two items? Because if we can estimate what we think that's going to be from literature, then we can at least have an idea of how we would move forward with giving you that sample size to make sure that you have enough power to be able to identify the results that you're looking for. So there's a lot that goes into it, but that's one of the things that we do as we talk to you for your statistics. And then that kind of all ties back together with this power analysis and sample size estimations. We would ask you what your research question is, and we would want to know, okay, what's the desired level of significance and your power level. And there is some discussion that has to happen between the clients and also your biostatisticians as you're working on this, because sometimes you need practical considerations. I've worked on projects before where they were looking at things that have very rare events, such as surgical site infections. And if you have very rare events that are happening, like a 1.8% of the time you're going to have a surgical site infection, we want to reduce that, obviously. But if it's a very rare event, that's hard to come up with a sample size to determine exactly a statistically significant difference between that and reducing that, because it's so small already. So those are some things that we would talk to you about for practical considerations and ask you, what is it that you're looking for, and how do you want to work through these issues with us so that we can help you get the best study designed as possible. And now I think we're ready for the first question. Can everyone see the poll?
I can.
Yeah, we've got
Yes.
8
Yeah.
or 53 who filled it out.
Okay, great.
53% rather.
Can we see the poll results?
Yep, I'll share it with you in just a moment,
Sounds good. Thank you.
for sure. All right. There we go.
You guys are all very smart.
Very good.
All right.
Okay, now we're going to switch gears of getting into specific types of statistical tests, really depending on the scenario. So whether you're working with continuous variables or categorical variables or the two together. And so we'll walk through these things carefully. So thank you. So we'll start off with continuous data, since that is, there are, some things to consider when working with continuous data. And so, in an ideal scenario, your data will follow a bell-shaped curve known as a normal distribution, but as we know in practice, that doesn't always happen. And so, of course, the central properties of the normal distribution include that most data points cluster around the mean, right? So, and with fewer points as you move further from it. And so the percentages under the curve show how data is typically distributed. So about 68% within one standard deviation, 95% within two standard deviations, and 99.7% within three standard deviations of the mean, right? And as I mentioned before, data doesn't always fit a perfect normal distribution. And so there are two main ways that data can deviate from this shape. One of them is skewedness. And so skewedness refers to the asymmetry of the distribution itself. And so the top right diagram here shows essentially three types of skewness. So you have positive, negative, and symmetric, which really help you visualize how skewness shifts the mean, median, and mode of your data. And so when your data is positively skewed or right skewed, your tail is longer on the right side, meaning that the values, that most values are on the lower end, but there are some higher outliers that you have. And then in negatively skewed data or left skewed data, your tail is longer on the left, with most of your values are higher up, right? But with a few low outliers. And so skewness is important because it does affect measures of central tendency, right? Your mean, median, and your mode, which we can see in the diagram showing how the mean shifts in your skewed distributions, right? So the second way that data can deviate from the normal distribution is through kurtosis. And kurtosis describes essentially the tailedness, how much of a tail that you have, or the peak of the distribution. And so in the bottom right figure, it shows essentially three types of kurtosis, right? You have leptokurtic, mesokurtic, and platykurtic. And so this comparison really helps to illustrate how kurtosis changes the shape of the distribution curve. And so your mesokurtic distributions are normal with moderate tails, right? And then your leptokurtic, which is the red here, have heavy tails with a sharper peak, meaning that you have more extreme values, making it a bit skinnier. And then you have your platykurtic distributions, which have lighter tails and a flatter peak, indicating that you have fewer extreme values. So it's a lot more wide. And so kurtosis, of course, affects the spread of your data because it really changes how your values are dispersed around the mean, right? And so recognizing skewness and kurtosis really helps us to understand our data better, which also helps us to choose the most appropriate statistical methods for analysis. And so if your data deviates significantly from normality, that would mean that you would require transformation or the use of non-parametric statistical approaches, which I know in practice, and I have seen this time and time again, where I struggle with an investigator to say, hey, your data is non-normally distributed, your continuous data is not normally distributed. We need to report a median and not a mean here. And I often get pushback of, well, this is how it's normally done in our line of work, on our area of research. People typically will report mean and standard deviation. And so my kind of a way that we sort of just are both happy is I encourage them to report both mean and median so that we're covering our bases, but noting that any statistician that will look at your work will know that your data is heavily skewed. So it's really important to ensure that you're using the right statistics and representing it in the correct way. So next slide, please. So now digging into, so now that we've covered the normal distribution and done a little bit of review there, we can dig into different types of tests. So starting when we're wanting to analyze continuous data with categorical groups. And so when your data is normally distributed, we typically analyze it, as I said before, using means and standard deviations. And so if you're specifically interested in comparing your means between two independent groups. So when our groups are not related, the appropriate test to use here would be a two-sample t-test. An example of this is maybe comparing average blood pressure levels between two independent groups. For example, like males and females are entirely independent, and you're comparing a continuous variable that you're assuming to be normally distributed. And for dependent groups, so when your two groups are related, and this is something like maybe a pre and a post measurement on the same individual, you would use a paired t-test. And so an example here would be testing whether there's a significant difference in blood pressure, maybe before and after a treatment within the same group. And then when you have three or more groups, when they are independent, we would use an analysis of variance, or ANOVA for short, to determine if there is a significant difference among the group means. And so an example here would maybe be comparing test scores across three different teaching methods, for example. And for dependent groups, we would want to use a repeated measures ANOVA, which is a very specific type of an ANOVA, or even perhaps linear mixed effects modeling. And so these are suitable for repeated measures, or if you have hierarchical data structures. And so, so for example, if you're testing for differences in exercise performance across multiple time points within the same group, these are the types of methods that you would want to use. So now if your data is not normally distributed, we would analyze it, of course, using medians and interquartile ranges, and use nonparametric tests as they don't assume a normal distribution. And so for independent groups, when you're looking at two groups again, you would use, so essentially the nonparametric form of the two-sample t-test is the Wilcoxon rank sum test, or a Mann-Whitney U test, which I've also seen used and is also appropriate here. And so when using these tests, you're essentially comparing the median income of, maybe, for example, comparing like median income between two independent groups. And then for dependent groups, again, the paired t-test, the nonparametric form of that would be a Wilcoxon sign rank test. And so if you were wanting to test for changes in pain scores before and after treatment within the same group, assuming that pain scores are non-normally distributed, you would use a Wilcoxon sign ranked instead of a paired t-test. And then lastly, if you have three or more groups, in independent groups, you would use a Kruskal-Wallis, which is the nonparametric form of the ANOVA, to look at differences in medians across multiple groups. And then lastly, for dependent groups, so the nonparametric form of the repeated measures ANOVA is a Friedman test, and where your data isn't normally distributed for a linear mixed effects model, you would extend that to a generalized linear model, or even perhaps transform your data when necessary. And so that is used for repeated measures or hierarchical data. Okay, so choosing the correct test, sorry, Tony, 1 second.
Okay. No,
Choosing the correct test based on the data distribution, your group structure, and research question is essential for you to answer your research questions. And if the data does not meet normality assumptions, opting for non-parametric methods ensures that you have both valid and reliable results. Okay. All right, good to go. All right, and so here is in a case where we have two continuous variables. So if our variables and the two variables that we're wanting to examine are both normally distributed, you would use a Pearson's product moment correlation. And so essentially this measures the strength and direction of what we're assuming to be a linear relationship between these two continuous variables. And so you can see here on the right-hand side, there's this figure here shows both the directionality on the top row here. So positive correlations pointing upwards, negative correlations pointing downwards, no correlation showing somewhat of a flat line or seeing your points kind of in not any particular pattern. And when you're thinking about magnitude of correlations, stronger correlations are more tightly around a line, forming a line, whereas weaker correlations are more spread out. And then, of course, there are instances in which variables that you think are linear actually show non-linear relationships. So in this case, showing a parabola, in which case you would have to, again, and descriptively, this is important for you to know and understand your data so that when you are analyzing it, if it is nonlinear, then the need to use nonlinear statistical methods would be appropriate here. And so in cases where you don't have normally distributed data and you're looking to analyze and look at the correlation between two continuous variables, or at least one of them is not normally distributed, you would want to use either a Spearman rank correlation or a Kendall rank correlation, which is a tau. And so you have your rho and your tau here, and these are computed a bit differently as it's relying on a ranking of values as opposed to the methods that are used for Pearson. Categorical. Are you suggesting that? Sorry, there's a question in the chat. 1 second. Are you suggesting that categorical ordinal data would be analyzed with the correlation? So ordinal data is something like maybe like an ordinal scale, for example. So an ordinal scale, like a Likert type scale, for example, that is measured on a continuum, you can use these Spearman rank correlations. But if we're talking about ordinal data, what is it? An example? I guess, these ordinal scales, like Likert type scales, are ordinal data. Tanya, do you have any thoughts here about?
Well,
So I don't know if I'm so ordinal data, I think in terms of Likert type scales can be appropriate for correlation, Spearman rank correlations.
Yeah, I would definitely agree, but it would also be, your other variable. I'm trying to think of an example because I feel like I've done one of these also more recently. But where both variables are numeric, but the one that's ordinal, you couldn't use the R correlation with it or the Pearson product moment correlation because it's not normally distributed.
Right.
And so, but if you're looking at a Likert scale with two variables, I mean, like two groups, now you're going back to what we were talking about before, which would be like your ordinal data would be non-parametric. So that would be like maybe the Wilcoxon, rank sum test or something along those lines. Yeah.
And I also think too that ordinal data is often thought as being categorical, and I think you can describe it that way as well. But oftentimes, and especially in statistical analyses, the categories are very imbalanced. And so oftentimes people will opt to analyze ordinal data on a continuum when and where it makes sense. So I hope I answered the question. Okay. So in terms of analyzing two categorical variables at a time, you really have two options, and the options really depend on the sizes of your sample size as well as the expected counts for each of the cells. And so Fisher's exact tests are generally work better for small data sets, small cells. And so both instances for a chi-square and a Fisher's exact, you would use these to determine whether two categorical variables are statistically dependent of each other. And so a chi-square test is used, and I know that chi-square is usually the first thing, and I think in my experience, people tend to use chi-square more than Fisher's exact. Even with small data sets, but I do want to put out some caution that chi-square test is not nearly as reliable with small data sets, and the assumptions of that test rely on the expected count, which has to be greater than 5 for each cell. So I do provide the computation at the bottom, which I won't get into. But in order to use the chi-square test, you do want to ensure that your sample size and the cell counts that you have are large enough to use this. And oftentimes, software that you're using will throw out warnings. And I know sometimes those warnings are ignored, but they should not be ignored. And you want to ensure that you're using the correct test. What about other exact tests? Like mid-P?
Do we have another question?
I think we do. I'm trying to read it. So what about other exact tests like mid-P?
I'm not actually familiar with the
I don't know about
exact
mid-P.
test.
Yeah.
Fisher's exact test. I actually use Fisher's exact test a lot because a lot of the data sets that we have, you end up getting into counts that have very small values. You can actually do a Fisher's exact test where one of the cells has a 0 in it, but you can't do that most of the time with a chi-square test because it really affects the cell count. And a cell having less than 5 in it, just the cell itself, is not the same thing as the expected count having less.
That's right.
But you're right, Alicia. I've seen that too, where it gives a warning that says 25% of your cells have less than 5% in the expected count. And then, oh, but let's still use the p-value. So just be very cautious.
Mm-hmm. Okay. But here's our next poll.
Got 7 out of 14 responses. Maybe get a few more.
What do you all think if you answer this question? Nobody sees who's answering the question. Just hazard a guess. Hazard a guess.
All right, here we go. And share.
Beautiful.
There we go.
Can't fool you
Everybody,
guys.
so smart.
All right.
And mine. There we go. Okay, so now we're going to jump from hypothesis testing and the types of statistical tests that we would use into statistics associated with treatment effect of outcomes. And we're going to talk a little bit about risk versus odds. I've always liked this example just because it's a very quick and easy example to explain the difference between risk and odds. So the risk is the probability a specific event will happen out of all possibilities. So if you want to know what's the risk of rolling a 6 on a single die, then it's 1 chance out of 6. So that's what the risk is. It's the number of people who have the particular outcome, or in this case, the 6, out of all the people that are at risk or out of all the outcomes. The odds ratio, however, is the ratio of the frequency of the event occurring to the frequency of the event not occurring. So the odds of rolling a 6 on a die are 1 to 5. You have a 1 chance of making a 6, and you have 5 chances of not making a 6. So that's the difference between the risk versus the odds of something happening. So when you're calculating odds, it's the number of people who have the outcome and over the number of people who do not have the outcome. A lot of times in mathematics, we would see odds written more with a colon in the middle, 1 to 5. But that's what it looks like, and those are the differences between those two values. And again, I think a die is a really quick example to kind of keep those in mind. So what do we mean with relative risk? I know there's a lot of words on this page, and so I'm just going to kind of go through it and we're going to hit the highlights especially, but we're looking at this example where we have this scenario. We've done a randomized control trial, and we're either giving drug A or a placebo, and we have 250 people total in the study. And in the drug A group, we had 20% that died, and in the placebo group, we had 24 people that died. And so we have 125 in each group. So the question is, what was the risk of death in the drug A group and the placebo group? So we're going to do the risk of each one. Well, in the drug A group, we have 20 people that died out of a total of 125. So that gives me a 16% risk of death from the drug A group. In the placebo, we had 24 that died out of 125, which is 19.2%. So this is how you would calculate the risk involved in either one of those groups. A relative risk, or what's called a risk ratio, is where we take the ratio of those two and we put them together. We make a fraction out of those two values. So we're looking at the ratio is the probability of the event occurring in the treatment group versus the probability of the event occurring in the control group. So when you do risk ratio, your treatment group risk is on top and your control group risk is on the bottom. So we've calculated this to be 16% for drug A and 19.2% for drug B. That gives us this value of 0.8333. So what does that mean? Well, the risk of death in drug A group is reduced by, and we subtract this because this is lower than 1. So we know that the risk of death is lower. A risk ratio of 1 means it's basically even. But here we have the risk of death has been reduced, and we've reduced it by 16.67% as compared to the placebo group. And that's what they mean when they talk about a relative risk. When we're looking at the odds, we're looking at what are the odds of death in drug A versus the placebo group. For drug A, we have 20 people that died, and instead of using 125 like we did for risk, we're using 105 did not die. So we have a 19.05% of odds for those that died in the drug A group. For the placebo, it's 24 that died and 101 that did not. So we have a 23.7% in the placebo group. Odds ratio, again, it's the fraction of those two put together, and the treatment is always on top, just like it is in risk ratio. So the odds ratio is the odds of the event in treatment group divided by the odds of the event in the control group. So we end up with an odds of being 0.804 by taking the treatment group and dividing it by the odds, the placebo group. We can interpret this two different ways. So one way is that the odds are 80.4 by multiplying this by 100. The odds are 80.4 to 100 that death will occur in the drug A group. Or we could say the odds of death is reduced. Again, it's less than 1. It's reduced by 19.6% for those receiving drug A as compared to the placebo. If the odds is over 1 or the risk ratio is over 1, when you subtract 1 from it, you're going to have, let's say it was 1.2. When you subtract that, you're going to get a 20% difference, and you would say 20%, it is increased by 20% for those receiving drug A compared to the placebo group. So the difference in the way you interpret this has to do with whether or not it's below that 1 value or above the 1 value, because that's going to give you an idea of whether it's reducing or increasing the likelihood. And then we have the number needed to treat or harm. And I'll be honest with you, I didn't even know this was a value that could be calculated until I got into medical analyses. And so I didn't even understand why you would have a number needed to treat, and especially didn't understand why you would need a number needed to harm. So I thought this was a very interesting take on this when I really did a little bit more in searching in this information. So we have absolute risk reduction. And that is used when the risk is beneficial. And then absolute risk increase is used when the risk is harmful. So in other words, it's calculated the exact same way. you're going to take the risk of the treatment group and you subtract it from the risk of the control group. And in this case, when we subtract these two, we're going to take the absolute value of that. So it's going to be a positive value at all times. And we're going to get 0.032. So that tells us that our absolute risk reduction, because our treatment group was lower than our placebo group, that means it was beneficial. So because it was beneficial, then it's an absolute risk reduction, and it is the number needed to treat. That's what's used when the risk is beneficial. And so we would do 1 divided by that. Again, it's calculated the same, but it means different things depending upon whether or not your risk in the treatment group is higher or lower than the risk in the placebo group or the control group. So in this case, 1 divided by that gives us 31.25, which is the number needed to treat to avoid, with drug A, to avoid 1 death. And now we have our Q&A. Looks like we're right on time. Look at that.
We do have a, sorry.
No, you go right ahead.
Yeah, we do have a question in the chat about consideration of period of risk, and whether that drives relative risk or odds ratio. And I can,
So go ahead, Alicia, I'm sorry.
yeah, no worries. If you, so yes, the period of risk really does, it can influence the decision between using relative risk or an odds ratio. And so from what I usually go off of is a relative risk is typically preferred when the period of risk is clear and you can measure incidence directly. And so that's usually best for cohort studies, especially when the outcome is not too common, it's rare. And so and what we're interested in is comparing the probability of an event occurring in one group versus the other group, right? And for odds ratios, this is often used in case control studies where the period of risk might not be as well defined, or where the outcome is rare and incidence can't essentially directly be measured. And so, and there obviously are connections between odds ratios and relative risk, and that odds ratios can approximate relative risk when the outcome is rare, but they tend to overestimate the association strength when that outcome is more common. And so if you do have a well-defined risk period and the ability to calculate incidences there, a relative risk is usually preferred because it is a more straightforward interpretation. But an odds ratio is often chosen for logistic regression models or case control studies when incidence data isn't directly available.
Thank you so much, Alicia. Any other questions? Feel free. I know it's 1 o'clock. If anybody has to leave, go right ahead and do that. If anybody has, if some of you have questions still, we can stay a few minutes longer to answer questions. And I know our speakers would be completely happy if you were to contact them afterwards with questions as well. So if you have to leave, enjoy the rest of your day and the rest of your week. If anybody else has questions, feel free to go ahead and unmute yourself. Put your video on or off, doesn't matter. Looks like everybody must be good, or they'll contact you later. Fabulous.
Yeah.
That was just wonderful. I'm sorry, go ahead.
No, just thanks again. That was great.
Fabulous job.
Thank y'all so much.